Okay, welcome to class. Quick announcement. Someone in the last TA session in the breezeway left a nice calculator. If this is you, come talk to me. So check if you're missing your calculator. It's yours, come and grab it. Okay, we'll start with our reading quiz for today. Okay, the reading quiz for today, the first question is, of all the crystal systems, blank is the most symmetric and blank is the least symmetric. Is the answer A, cubic and triclinic, B, hexagonal and triclinton, C, tetragonal and orthorhombic, or D, monobombic and hexagonalgor? I did not write these. It's definitely my TA's.
I sent you my ID thing, and apparently you said it still didn't work.
There's about 10 students that I still can't fix it for. Don't worry, at the end of the semester, I am keeping track of your points. It's just not ever going to show up on Canvas, but I can manually do it. Okay. But if you ever want to check and see how your points are doing, you can swing by my office and we'll pull it up and take a look at it. It's unfortunate. Should I fold the corners? Should I seek a safe one? Do what you gotta do. If you fold the corners, good luck. Okay, we're gonna end the poll on this one. A, B, C, or D. People think definitely A. Okay. I apologize, that drawing is lower resolution than I wanted. Consider the figure below with the directions shown in red. Which of the following are true? This point, it starts right there at 1/2 the way along this line, and it goes backwards into that unit cell up to intersecting 2/3 the way up the z-axis. Okay? The question then says, which of the following statements are true? A, it has a component in the y direction. B, it has a component in the x direction. C, it has a component in the z direction, or all of the above. Yeah, question?
Where's the origin?
The origin is in this back corner. By definition, that's where we always put it. The final point, sorry, just to clarify, it begins down here on this front bottom edge, and it ends on the back face on that back edge over there. The back left edge, vertical. Okay, we're going to wrap it up. Okay, definitely has all three components. Then the last question is, the magnetic properties for some alloy are anisotropic. This means that A, they're made of many small crystals. B, they're made of one large crystal. C, their magnetic properties are not direction dependent. Or D, their magnetic properties are direction dependent.
Oh, wait,
Okay, we're gonna wrap up the poll. Answers in A, B, C, or D. Okay. Okay, correct. That's right. Okay, what are we going to learn today? We'll pick up where we left off. We did last time the FCC and the BCC crystal structure. We're now going to do the HCP. We'll learn how to calculate the theoretical density for any of these things. Then we'll get into using the cation-anion ratio to predict what structure forms. That's actually pretty cool stuff. We'll briefly talk about silicates and what's the basic building block of all silicate structures, which are kind of complex. And hopefully by the end of class, we'll have time to get into the different crystal systems and even use Miller indices to label directions and planes and so forth. So let's start with HCP. HCP stands for hexagonal close packed. So this structure is not cubic, but it is equally as densely packed as the face-centered cubic. Last class we did that calculation. We calculated the atomic packing fraction for FCC. We found out that it's 74%, meaning 74% of the volume in that crystal is occupied by atoms, and the remainder is empty space. Well, hexagonal close packed is the exact same. Because you now have a hexagonal unit cell, we don't have just one lattice parameter. In a cube, all three sides of the cube, on the edges, those are all just equal to A because it's a cube. Now we have to have two different lattice parameters. So we have A and we have C. Moreover, you have the top and bottom plane, which we call the basal plane. So I'm talking about this region right there. That whole plane on the top there, that's what we call a basal plane, right? We'll learn how to label that later today, I hope, right? So the first question is with this, is what would be the coordination number for hexagonal close packed? All the spots where you see black circles represent where an atom would exist here, including these light gray ones in the center. Those are also atoms. So what is the coordination number, meaning what is the number of atoms that are nearest to it, right? So we have a vote for 6. Anybody differ?
That's wrong. That's wrong.
6 is a good guess. It's not right. I think 12. Okay, for FCC, what was it? FCC was 12, and this is equally as dense, so a good guess might be that it's going to be the same number. So let's go ahead and start counting them. Let's pick an atom. Let's take this one and say, let's take this one for a moment. That one has 6 that are right around it at the same length, right? Now the hexagonal close packed can be thought of making an arrangement of spheres that look like this. You draw them just as if you were, trying to stack marbles or oranges or whatever as closely together as you could. You would get a hexagonal arrangement, and you build up a layer like that, and then when you're going to build another layer on top of it, you have 2 choices, and we'll come back to this probably tomorrow. But you can either choose to put it on these triangle pointing up spots or on these triangle pointing down spots. Right? You have to choose one or the other. You can't put it on both spots. For example, if I put them on the triangle up spots, then I'm going to stack it like so. Right? But if I chose to put it on the triangle down spots, that whole second layer would be shifted over by a little bit. Are there any questions on that? Because of that, we're considering this atom right here. It's clearly got 6 atoms that are equidistant on either side of it. It's just the atom... It's 2 of the radii, right? Because they're touching. Now, if you stack it like this and you do the algebra, or the geometry, I guess it would be, you can figure out that the layers above and below are also equally distant. They're touching, so it's still just 2 radii away. Therefore, these 3 atoms below it, they are the 3 that this blue atom is sitting. They're like the 3 red atoms that blue atom is sitting on top of. You guys see that? And on top of it, you'd have 3 more above it. So what's the coordination number? You've got the 6 that are in plane, then you've got 3 below and 3 above, so it's 12. Just like with face-centered cubic, you also have 12 for the coordination number here, okay? Now, whether or not you chose, like, as I mentioned, this triangle up or triangle down, we'll come back to that. It's called the layer of stacking, and it'll be important later. We'll come back to it. So 12. All right, let's talk about how to calculate density. This will definitely be on the second midterm. Yeah, question, Logan?
Yeah, what was the coordination number for BCC?
What was the coordination number for BCC? Let's go back to it and take a look at it. BCC is right here. So take this middle atom. What's the number of atoms that are equally close to it and closest? It'd be 8, yeah. And again, if you chose, just like with FCC, it didn't matter whether you chose either position. If you chose this one and you counted the atoms nearest to it is sharing 8 different unit cells, right? This atom is 1/8 of the way into this unit cell, but there's 8 other unit cells that it's also in. And at the center of each one of those is an atom. So it also has a coordination number of 8, right? So it didn't matter which atom you chose there. All right, how do you calculate density? This will definitely be on midterm 2. Here's how it works. Density is just mass over volume. You've known this forever, right? So to calculate density, we need to figure out a way to consider the mass of all the atoms in the unit cell, and then we need to divide it by the volume of that unit cell. That's really all it is to it, right? Because you don't know the mass of atoms in terms of just like grams, we almost always do grams per mole, right? Then because of that, you need to have Avogadro's number in the denominator. So it's going to be Z will be the number of atoms or molecules per unit cell. M's of W, that's the molecular weight. VC is the unit cell volume, and NA is Avogadro's number. So let's do it for FCC really quickly. FCC, that's face-centered cubic. Again, that's this one where it's a cube. You've got atoms at all the corners, all 8 of those corners. And you've also got them on the 6 faces. 1, 2, 3, 4, 5, 6, right? Again, those would all be the same type of atom. I've drawn one small and one larger just for clarity a little bit. So how many atoms are there per unit cell? We calculated this last time. How many were there in the FCC lattice? 4, right? There's 8 times 1/8 on the corners, plus 6 faces, each half in. 6 times 1/2 is 3. So 3 plus 1 is 4. So if we were going to calculate the density of this, we'd start out by saying, okay, there's 4 atoms. The next step, you'd have to know, well, what type of atoms are these? Let's say that it's copper, right? Or which one did we do last time? Was it copper? Okay, copper. And we know the lattice parameter is 3.601. That's good. So let's do this. Let's say, okay, it's copper. So the lattice parameter, the volume of the unit cell is going to be 3.601 angstroms cubed, right? What's the mass of copper, molecular weight of copper? Anybody have that on hand? 55 or something? Anybody have that? Somebody find that. What it? 53? Oh, 63.546. That's grams per mole. Okay, so we've got the number of atoms, we have the molecular weight of copper, we have the volume of the unit cell, because in this case it's just cubic, so the volume is easy, it's just A times A times A. And then we need 6.023 times 10 to the 23 per mole. So go ahead and plug this in and tell me what you get for density. So work this out. We almost always report density in grams per centimeters cubed. Sometimes they do kilograms per meter cubed, but in this class, just report it in grams per centimeter cubed. So you need to convert angstroms to centimeters. Again, an angstrom net is 1 times 10 to the negative 10 meter. That's weird. Yeah.
I just have a question regarding BC. That's the volume of it. Oh, never mind.
Volume of the unit cell, yeah. And again, we're doing cubic right now. For hexagonal, you have to figure out what's the volume of that hexagonal prism, and we'll show you that a little bit later.
Running it back into
Okay. Anybody else getting that? I get 9.03. Somebody else? So it's not bad. This is actually a pretty good estimate. Now let me ask you this. Why is the actual density, it looks like it's maybe 1 or 2% less. Why would the actual density be slightly less than the theoretical density? Yeah, what do you think?
Flaws? Like empties?
Say one more time.
Vacancies?
Yeah, vacancies, which we haven't covered yet in this class. We're going to come back to that. Basically, where you expect an atom to be, it might not be there. What else might account for this difference in density? Yeah, what do you think, Matt? Yeah, it could absolutely do with temperature. We know that things, as you heat them up, almost everything expands. And so when we've given you this value of the lattice parameter, this distance right there, that's the 3.601. I have no idea where that, angstroms, right? I have no idea where that value comes from. What temperature was that taken at, right? So when they report the density changes as a function of temperature because this thing does expand, but it doesn't add or delete atoms. Well, it kind of does. When we talk about vacancies, we'll come back to that. Yeah, comment?
Would gravity have anything to do with the density at all?
So, good question. Since this is grams, right, as opposed to like, say, so if it was newtons, right, so imagine like when we go from pounds to newtons, you have to use gravity there, right? But this is just grams, this is just a mass, so gravity will not come into play. Yeah, the mass doesn't change, it's not influenced by gravity. The force that gravity exists on something is proportional to the mass, right, but this is just the mass. Any last question? Yeah, Rosa?
Can you write out the math that you get after you divide? How do you convert to?
Okay, the conversion step that you want to use is this. You're going to end up with an answer in, let's say that you converted angstroms to meters, right? So you're going to get some number in grams per meters cubed. To turn that into grams per centimeter cubed, you need to recognize that there are how many in 1 meter, how many centimeters are there? 100 centimeters. But we were talking about cubed quantities, so you need to cube that whole thing and cube that whole thing. So that will allow you to convert. So basically, you're going to need to divide your answer by 100 cubed. That's assuming that you converted angstroms to meters already. If that's not the case, you'll need to do that still. Okay. Okay, there's one other thing that can change density, which is not just individual atoms missing, but big globs of atoms missing. We call these pores, right? Cracks, pores, something where you just have, my material science students, they did this the other day when they casted the molten metal. Even though you'd think molten metal would fill it entirely, if you were to break those things in half, you might actually see some tiny pores in there where, for whatever reason, there was an air bubble that just didn't get out, okay? But that's pretty darn good. It's a pretty great way to estimate the density of things. So being able to calculate theoretical density from crystal structure, guarantee it will be on the next midterm. And probably for a more complex thing, not just a single metal. It'll probably be for a compound. Speaking of compounds, let's talk about ceramics. Ceramics are not just pure metals. I mean, some of them are, like carbon. Diamond is a ceramic, and it's just pure carbon. But most of them are ionic compounds where there's 2 or more different atoms coming together. When you have 2 or more different atoms and they're ionic, that usually means that you have the giving of an electron, right? The sodium really doesn't care about that electron, so it just gives it to the chlorine, right? So you form positively charged ions, which we call cations, and you form negatively charged anions, right? And you can predict what structure is going to form from the size of these 2 species. Here's how it works. A stable crystal structure will have the positive and the negative ions touching one another, right? There's a Coulombic attraction. They want to be drawn close together. So, for example, if you take this scenario over here, that the ion in the middle is going to be the cation. They're always smaller. They've lost electrons, so it shrinks, right? That is so small that when you take this arrangement of anions around it and they're touching, so they can't come any closer together, the cation is not touching them, right? So that is what we call an unstable configuration. So that probably won't form. Meanwhile, over here, you have this ideal ratio where the anions are touching one another and the cation is touching all of them. So that size is what we call the ideal ratio. And then this can be, if it's larger than the ideal ratio, as long as the negative and the positive ions are touching one another, that can still be stable, right? So imagine if I drew it even more exaggerated. Let's say you've got this scenario, right? You've got these 3 anions, right, that are really quite large, and then you've got a really small cation in the center, right? So basically our cation got even smaller, and because it got smaller compared to the anions, it can only be surrounded by 3 anions, right? If the cation's a little bit bigger, we could surround it by 4. If it was even bigger, we could surround it by maybe 6. If it's even bigger, it could be surrounded by 8, 12, and so forth. So this was the first thing that some clever people realized. They said, okay, if you just calculate the ratio of the cation divided by the anion, this is this RC over RA ratio. If you take that, and it's going to spit out a number. Based off of what that number is, you can predict what the geometry is going to be, right? So if that number is anywhere less than 0.55, this is going to be a linear geometry, meaning that the coordination number for the cation is going to be equal to 2. It can only be surrounded by 2 anions. And this might look like this. You have a huge anion, you can only put your cation right between them, okay? If it's between 0.155 and 0.225, your coordination number is going to be 3, and we call this trigonal. If it's between 0.225, 0.114, now you can have tetrahedral. Tetrahedral, meaning it's surrounded by 4. This can be octahedral, which does not mean 8. It means 6 coordinated. The oct comes from how many sides that creates. So again, so if you got 4 atoms in the plane, 1 above and 1 below, you form this 8-sided, like 2 pyramids on top of one another. So that's why they call it octahedral. It has 8 planes in that sort of shape, but it means it's surrounded by 6 ions, okay? And then finally you can do, I think they just call this cubic geometry, okay? And then 12 they call dodecahedral. Dodecahedral, right? So this is useful because we can look up the size of ions, right? I can look up, and for my periodic table, for a lot of these things it's known. Let's say chromium. Chromium, as a function of its charge and its coordination number, you can look up what its ionic radii should be. So if it's chromium oxide, you could start to predict what crystal structure would form. Now it's a bit of a chicken and an egg, because in order to, like the ionic radii depends on the coordination number, but you're using this to predict coordination number. So it's a bit of trial and error. On a test, what I'll do is I will tell you, I'll say the coordination number, well, the ionic size is this and this, predict what coordination number is, and then predict what crystal structure that is. So how do you do that next step? Let's talk about that. Any questions on this so far, though? That basically the size ratio between these 2 ions should indicate roughly what the surrounding environment should be. Yeah?
This is just for ceramics, right?
This works for, I mean, they use it for ceramics. It should be a universal principle, but it has to be something that has a cation and an anion, and that's generally speaking ceramics. Yeah? Yeah.
So if it's, for example, trigonal, it means that the Cn will be equal to 3.
One more time.
If the geometry...
Oh yeah, coordination number would be 3. It's surrounded by 3. And we call that trigonal. If it's 4, tetrahedral, octahedral, cubic, dodecahedral. Okay? So let's talk about our first type of ceramic structure, and it's called the rock salt structure. Rock salt is the same stuff that you salt your potatoes with, right? It's just sodium chloride. The crystal structure, like the mineral name, is rock salt. How it ranges is you can think of it as 2 interpenetrating FCC lattices, right? So there's 2 different types of atoms here.
What is AX structure type?
That means that you have 1 cation and 1 anion, that it's a 1-to-1 ratio. We'll come back to different, like there's AX2 or A2X structure types. We'll come back to that. It just means right now that there's a 1-to-1 ratio. For every sodium, you've got a chlorine. So if you look in this, you've got your sodium and your chlorine atoms. Again, I guess the large one would be your chlorine and the small one would be your sodium, because the chlorine it picked up an electrons, so it's going to be bigger. If you were to plot this, it's easy to see that sodium is face-centered cubic, right? These ones are at the corners. And they're also at the faces, front, back, left, right, top, bottom. But if you were to shift the origin over by half of a unit cell, oh, lost it. Not today. I promise I'm getting this fixed over fall break. If you shift that over by half a unit cell, you could create another FCC lattice with the chlorine atoms. Is that easy to see? If we draw another unit cell over right here, that would now be the lattice parameter. So you would have corner atom, corner atom, corner atom, corner atom, and that would be now a face atom on that front face. So this is just two interpenetrating FCC lattices. Okay. Any questions on the rock salt structure? The coordination number, meaning how many atoms it's surrounded by, for both cation and anion is 6. Right. So you could actually see that if you pull up, say, this atom in the center. It is surrounded by 1, 2 on the top and bottom, then left and right, 3, 4, front and back, 5, 6. You could do the same thing with any gray atom. They each have equal coordination numbers. Okay? So for this, we could figure out the density of this structure. We could say the density should be equal to Z times the molecular weight divided by the volume of the unit cell times Avogadro's number, just like before, except what do we have to do differently this time? Well, this whole thing, that is our lattice parameter A. So A is probably going to be larger than it was to take the copper. What else do we need to take into account? Well, you've got two different types of atoms. You can't just plug in copper. You have to plug in sodium and chlorine. And how many formula units are there per unit cell? Well, if you count just the sodiums, there's 4. And then, again, you could count the chlorines. Counting them is a little trickier. You've got 12 along these edges, and those edges are a quarter of the way in. So you've got 12 times 1/4. I'm talking about these things. The ones along the edge centers. Those are 1/4 of the way in, and there's 12 of them. And then you've got 1 in the very center. So you've got 12 divided by 4, that's 3 plus 1 in the center. So there's also 4. So there's 4 chlorine atoms, and there's 4 sodium. In other words, there's 4 molecules of sodium chloride, right? So when you do this, when I calculate density, how I suggest you do it is to write 4, because there's 4 molecules, times the mass of sodium, molecular weight of sodium, plus the molecular weight of chlorine, divided by A cubed times Avogadro's number. Any questions on doing this? Yeah, Arthur.
I just had a question regarding the ratio when it's larger than 1. The dodecahedral.
Dodecahedral. Here, let me show you what it looks like. Dodecahedral coordination. Dodecahedral, it's 12. The coordination number is 12, and it looks like, let me show you a good one. None of these are very good. I can post one after class. I'll put it into the notes. It basically is surrounded by 12 at equal distance. Any questions on rock salt? Can we move on? So rock salt's the simplest ceramic structure. Brad?
How would you solve for A?
How would you solve for A? It's a great question. That's actually a really great question. What should A be in terms of the ionic radii? If you know our sodium and our chlorine, radius of chlorine, and you know the radius of sodium, could you write an expression that is A in terms of those two things? Maybe take a stab at this. Imagine this thing's going to shrink until they touch. Where might they touch? And therefore, what should be A as a function of the chlorine and the sodium radii? So maybe work on that together. And we've got some TAs you need a hand.
So only if it's stable.
Meaning they're touching. Exactly. Okay, anybody want to take a stab at this? How might you write A as a function of RCl and RNA? Anybody? No. So where will they touch? Maybe that's the first question. Where will they probably touch? Probably like right along this edge, right? They're going to touch. So this goes from 0% of the way across that edge length. This is halfway percent of the lattice parameter, right? So you could say that half of a lattice parameter should be equal to the radii of those two things added together, right? All right, let's go to our next crystal structure type. This is the cesium chloride structure type. And why do they call it cesium chloride? Why do they call the element rock salt? Just because that's the first one that they identified that has this type of structure. And thereafter, they always called it after that first name. So cesium chloride, this time the coordination number is 8 for both the anions and the cations instead of 6, right? You can think of this as two interpenetrating simple cubic lattices, right? So a simple cubic lattice would be like this one here without the green thing in the center, right? That would be a simple cubic lattice just on the corners. But if you put one in the center, you might say, oh, that's just BCC, that's body-centered cubic. I've seen that before. But it's not body-centered cubic because these are two different atom types. In order for it to be body-centered cubic, they'd have to be the same type of atom. And so some metals can do that because it's all one type of atom. But when you come to ceramics and you've got two different types, we have to call this a different type of structure. And this is now the cesium chloride type of structure, right? So that's cesium chloride versus sodium chloride structures, right? Let's do the next one, which is zinc blende. The zinc blende structure, that's the name of the mineral for zinc sulfide. Now you have coordination number of 4 for both the anions and the cations. And again, this looks like two interpenetrating FCC lattices, but instead of being shifted along the edge length, remember for this with sodium chloride, it looked like two lattices, but we'd shifted it by half of a lattice parameter in that direction. Now it looks like we've shifted it by a quarter of a lattice parameter in both the X, the Y, and the Z directions. So basically this is an origin and that is an origin for the two different atoms. So again, to clarify where that's at, if you were to draw a line from this back right top atom up here and you were to draw that all the way down to this front bottom left atom, that gray atom would be 1/4 of the way along that line. Gray is 1/4 along the body diagonal. Can I answer any questions about that? I'll bring in some models next class and it might make these a little bit easier to see. Yeah, question?
The bit about like saying that the Y and the X zero are shifted, how do you know that? Where is that coming from?
So this one's easier to see if you look at multiple unit cells. Let me pull it up real quick. Let me pull up zinc sulfide. Okay, so this is a software called Vesta, which you're going to learn how to use on your next homework, actually. Yeah. The joy. You will love it. It's free. It's awesome. What it does is it allows you to plot these structures, and it makes it easy to see multiple unit cells. So let's go ahead and we're going to change our boundary. Instead of just looking at one unit cell, let's look at 2 unit cells in the X and the Y directions, right? So now we went 2 and we went 2, so there's 4 unit cells there. Now if you look at this, it's a little bit easier to see that there's 2 interpenetrating FCC lattices. You've got the one FCC lattice with yellow atoms, here's your corners, that's your front face, bottom face, left, right. But you could also have another lattice, these would be your corners with your gray, right? That would be bottom face, front face, and so forth. Make sense? So it's shifted by a quarter of the lattice parameter in the X direction, a quarter of the lattice parameter in the Y direction, in the Y direction going backwards, and a quarter of the lattice parameter going in the Z direction. So if you look at that on an angle, it's actually, let me clean this up just a little bit. Let me go back to just one unit cell to not overwhelm us. Again, so where is, again, that's that atom that was in that front left corner. It's along that body diagonal. See how that lines up along that body diagonal? It's 1/4 of the way along the body diagonal. Can I clarify that anymore? Yeah.
So within the cube, any diagonal you create, only one gray atom intersects that line, right?
Sorry, one more time. Any
diagonal that you create within the cube, like when you
yeah, that's a really good question. That's right where I want to go next. If you look at this is actually a pretty open crystal structure, right? See these big open spots like right here and right here, or if I rotate it this way, right there and right there. This structure has some big open spots in it, right? So if you remember a couple homeworks ago, this was the diamond crystal structure, and we said that liquid diamond was more dense than than diamond, right? Liquid carbon was denser than diamond. The reason for that is that carbon can only have how many bonds when it's bonded to itself? It can have 4 bonds, right? So if you look at this, imagine that these were all the same type of atom, right? If these were all carbon, then they would be bonded to 4 other atoms, right? If we were to, even though there's room for it, if I was to put another atom right here in the middle, that would cause this carbon to have like a 5th bond, which is not allowed. So diamond actually is what we call an open structure as opposed to a closed packed structure because of the bonding requirements. So it creates it. We know that it has to have a coordination number of 4 because of the size of these things, and it creates this open crystal structure, which is why when you melt diamond, it would actually be denser. Now, another crystal structure that forms in this exact same structure is silicon, and you can melt silicon at not crazy temperatures, and solid silicon would float on liquid silicon. You can actually see that. Yeah, question?
So diamond is like CQ a lot of times, right? Is that because it's open, or is that something?
No, that's something else. We'll come to optical properties at the end of this semester, unless you're civil, and then you'll always just wonder why diamond is CQ. Okay? So again, that is 2 interpenetrating FCC lattices shifted by a quarter of a lattice parameter in all 3 directions. Can I clarify that anymore? What would be here's a tricky one. How would you relate the lattice parameter to the size of these 2 anions, or 2 ions, right? So what is the relationship between A and the size of, say, your zinc and the size of your sulfur atoms? How would you write that? Again, remember, they touch. Where do they touch? Along that body diagonal. And how long is the total body diagonal? Somebody remember that from last class? The total body diagonal, it was root 3 times A. And then if we're going a quarter of the way, that's divided by 4. That will be equal to the radius of your zinc plus the radius of your sulfur. And again, if you look up values for zinc and sulfur with coordination number 4, you could predict the lattice parameter of the structure, and it's going to be pretty darn accurate. Okay? Keep going.
What does that equal then?
These are just equal to one another.
Okay.
Sorry, the square root of 3 times A. Let me just move this so I can write that a little clearer. Root 3 times the lattice parameter divided by 4, meaning a quarter of the way along that body diagonal, should be equal to the radii of your cation plus the radii of your anion. You could write zinc and sulfur, but this is a generic crystal structure type. More than just zinc sulfide crystallizes in this type. Okay, keep going. More mysteries of crystal structures. Okay, let's move to now the AX2 type. The AX2, now we're going to depart from a 1-to-1 stoichiometry. We're going to say that it's a 1-to-2 ratio. And the first one would be the titanium dioxide, right? TiO2. So you've got 1 cation, but you've got 2 anions. So if you were to look up the RC over RA, the radius of the anion and the radius of the cation, and you were to plug that in, you would get a number that corresponds to a coordination number of 6, right? The size of titanium's a little bit bigger. When you divide it by oxygen, it leads to a coordination number of 6. So that tells you right off that this must be the titanium in the center there. That's got to be titanium, right? Because it's surrounded by 6 oxygens. However, oxygen is not surrounded by 6 titaniums. How come? Oxygen is surrounded by 3 titaniums, whereas titanium is surrounded by 6 oxygens. Why is that? What do you think? It's commonly, right?
Yeah. You can't make that many bonds.
Good guess. It's not reason. There's room. Again, if you rotate this crystal structure, there's room in there that you could cram in more titaniums. There's empty spots. Yeah, Spencer?
Because the oxygen has a -2.
Yeah.
Titanium has a minus.
It has to do with the ratio, right? Titanium is 4+ and oxygen is 2-. So there has to be twice as many oxygens as there are titanium. Or in other words, we have to have missing spots where we could put a titanium in there. There's room for it. But because of charge neutrality, we have to have half as many titaniums as there are oxygens. So when you calculated this and you figured out, okay, my cation is surrounded by 6 anions, you know immediately, due to the charge difference, that your anion can only be surrounded by half as many, so 3. Okay? Make sense? Should keep going. So rutile, this is white, by the way, this is white paint. All this white paint, any white paint is probably rutile, because titanium dioxide's all over in the dirt, and so it's easy and cheap to mine, and it's bright white. Okay. Now let's move to a different structure type. You know, there's tons more. I'm skipping a ton of things here, right? Because this is just an introductory class. There's lots and lots of other AX2 types or A2X types. Let's go to the ABX type structures though, right? So now you've got two different cations, A and B, and one anion. And the most important, the most technologically important crystal structure out there is called the perovskite crystal structure, right? Examples of it are barium titanate, which is something called a piezoelectric, which we'll come back to later this semester. Just super, super important materials. Again, you've got two different cations. You've got, in this case, the barium and the titanium, and then you've got one anion, which is the oxygen. Because there's three oxygens, right, so there's A, B, O3, the oxygen's almost always going to be -2. So therefore, you have to account for a -6 charge coming from your anions. So with those two cations, A and B, you have to add up to +6. And it doesn't matter how you do it, right? You could have +1 and +5. You could have +2 and +4. Or you could have +3 and +3, right? So because there's so many different type of ions that can come together, that's what makes this such a flexible crystal structure. And that's why so many crystal structures crystallize so many different compounds crystallize in this crystal structure. Because it's just so flexible. You can have lots of different ratios of charges and whatnot, okay? So in general, here's the rules about this one. The A site is where your bigger cation goes. The reason why is because it is a 12 coordination site. It's surrounded by 12 ions. Again, we're talking about this orange thing. This orange atom is surrounded by 12 atoms, its nearest neighbors. The nearest neighbors are what the green ones here, or sorry, the gray ones. Again, in one unit cell, you've got 1, 2, 3. Sorry, I can count here. 1, 2, and 3, right? But that's in one unit cell, and we know that since that's a corner atom, it's sharing with 8 other unit cells. So at first glance, you should say, oh, it should actually be coordination number 24, right? 3 per unit cell plus 8 times 8 unit cells. That should be 8 times 3 equals 24. So why is it actually only 12? The whites are sharing. They're on faces, so they're half in and half out on their cell. So it's 12, or it's 24, but you have to divide that by 2 because they're half in and half out. So yeah, that one's coordination number of 12. And again, if we wanted to, we could pull that one up. Perovskite, and you could see it. Let me back out a little bit on this. So the green atoms are our crystal, are the perovskite, the 12-fold sites. And if you count those red bonds coming out from it, there's actually 12 of those. Let me make it clearer by deleting out the other ones. And then I'll click this to polyhedral view. So the person who asked what a polyhedron looks like, those are all dodecahedral polyhedrons. They're 12-sided. Right? Okay. Okay, so the big atom sits at the corners. The small atom, the small cation, sits at the very center. And then you have this octahedral coordination of oxygen atoms around that smaller atom in the center. Okay? So oftentimes, instead of showing it like this, a better way to show this crystal structure is to not show that, but instead to show the octahedra. Right? So they'll show that thing, and if you draw multiple unit cells of this, let's say we want to draw 3 in each of those directions, all of a sudden you can see how this crystal structure forms, right? You've got the big atoms sitting at the corners, and then you've got the titanium surrounded by oxygens. The fact that it's a relatively small atom like titanium in the middle of that oxygen net is why this creates such awesome properties. Piezoelectric and high dielectric constant. Again, we'll come back to those later this semester, but these can do really, really interesting technological things for us. And they make really cool stuff happen. So we'll come back to them. Okay. Now you can have an ideal perovskite or you can have a non-ideal perovskite. In a non-ideal perovskite, instead of these things being lined up perfectly in sort of that rigid matter, they can be tilted. So see, here's the ideal one on the left. Or those things can be tilted, and that's the one on the right. To figure out whether or not it's going to be tilted, you can calculate what's called the tolerance factor. The tolerance factor, you're just plugging in the radius of your A atom, your oxygen atom, and your B atom. And basically, if it equals 1, then you'll have an ideal perovskite. And if it's not 1, you're going to have something distorted. Okay? Rosa?
How do you know what's it tilted relative to?
So see here, let me focus along the A direction. These things are lined up with the axes. right? They're vertical. If I look at along the B direction, it's like that. And the C, these things are they're forming a square. When it tilts, this whole thing rotates counterclockwise or clockwise one to another. And what that does is it decreases the size for this atom. Let me show you what I mean by that. You can have an arrangement of these diamonds, which is perfect. Kind of perfect, right? Or you can tilt them, right? Let's tilt them by making it elongated, right? When you do that, you end up with this sort of arrangement. Give myself some more room. Right? And by doing so, you made this opening smaller. So it can accommodate a smaller atom there. So basically, why does stability happen? Stability happens because these things want to be touching one another. And if they don't, they'll oftentimes tilt in exaggerated ways or extend and get longer in order to make that tilt possible. Okay? Let's hold on to that thought. When we get to piezoelectrics, which is an interesting electronic property, we'll come back to that because whether it transitions from the ideal to the tilted ruins the performance of that device. So we will come back to that later on. Okay, then the last thing we're going to cover today in the last 5 minutes is silicates. Silicon is one of the most abundant elements on this planet, so it's not surprising that if you go outside right now and grab a handful of dirt, a ton of that is going to be silicon or silicates, right? It's not going to be the metal silicon. It's going to be silicon bonded to oxygen, right? So silicates, what they have in common is that the silicon is bonded to the oxygen, and the way that silicon bonds with oxygen is it forms this SiO4 tetrahedral unit. That's the key thing to remember. All silicates have these little tetrahedra. Remember, tetrahedra, that means 4 sides, so it's one of these things. You've got the silicon in the center, and you've got the 4 oxygens around it. So that's a SiO4 tetrahedral unit. And if you do the math, silicon is going to be +4. Oxygen, there's 4 of them, they're -2 each. So it's +4 and -8. So that doesn't add up. So in order for this thing to be charge balanced, you have to start sharing with one another, right? You can start sharing oxygens, like these 2 tetrahedra are sharing to form a disilicate ion. And that went from being, now you've got Si2O7 6-. They can share in a repeated fashion, like a chain. That's Si2O6 4-. They can form sheets, and now you've got Si2O5 2-, right? But you basically start putting these things together. Okay? This is the basis of so many materials. Say, take this one for example, kaolinite. Kaolinite is clay. That's one of the most common forms of clay. In clay, you've got the SiO4 sheets, right? Those are sharing just like this guy right here. Basically those layers. But because that's still negatively charged, you have to introduce some positive charge. They have a layer, this is an aluminum hydroxide layer, which is slightly positive. So those two together compensate and you have charge neutrality. We're not going to get into this in any more detail than that. All I want you to know is that silicate structures form with the SiO4 tetrahedra that typically link together in some sort of way. That's all you need to know for that. And I guess we got a little time. Let's talk about carbon real quick. We already said diamond. This structure looks just like zinc blende, except that in zinc blende, we had the yellow and the gray. In diamond, it's all the same atom. It's the same crystal structure in terms of where the atoms are located, but diamond, it's all one crystal structure type, all one atom type, as opposed to 2. And we'll pick up here next time. We'll finish carbon next time.